Some limits involve x approaching infinity, and these are called end behavior limits. We can't use substitution for these because infinity is not really a number; it's an idea, it's a concept. We can we can use substitution if we just imagine not plugging in infinity itself, but a number that's really, really big, or if you're going to negative infinity, a number that's really, really big in the negative, on the negative part of the number line. But rational functions are good tools to sort of develop your analytic skills when dealing with end behavior. And so the key thing to note is that in the long run, if I look at this problem 1, x squared minus 3x plus 1, in the long run really just starts to behave like x squared. And in the bottom, 2x to the squared plus 5, in the long run really just starts to behave like 2x squared. So this answer is going to be the same as just analyzing that ratio, the limit as x goes to infinity of x squared over 2x squared. And once you identify that, it's easy to see that the x squareds would cancel, and this is just the limit as x goes to infinity of 1/2, which is just 1/2. Okay, so that'll generally always happen when the degree of the numerator and the denominator are the same. It just ends up going to the ratio of those leading coefficients. In number 2, similar idea. The numerator in the long run, as x goes to infinity, really just starts to behave like 3x cubed. And in the long run, the denominator just starts to behave like x to the 5th. So this answer is going to be the same as this answer. And here, there are a few options. One is to just notice that if you plug in a really big number into this expression, the denominator is going to get bigger more quickly than the numerator. And when the denominator gets bigger quickly, then the whole expression goes to 0. Okay, so this is going to go to 0. Another option is to do a little bit of division first. So there's an x cubed at the top and x to the 5th at the bottom, so this would cancel and I'd be left with an x squared at the bottom. So you can change the problem if you don't see it right away. You can change it a little bit, take it one step further and write it like this. And now what you can see is that the numerator clearly is going to go to infinity, and therefore the whole fraction is going to go to 0. So that the answer is just 0. Okay, so notice we're not plugging anything in, but we're using a little bit of our number sense and our ability to reason how numerators and denominators grow compared with each other as x approaches a value or an idea such as infinity. And how about this last one? Same idea. We can limit our analysis to the leading term of the numerator divided by the leading term of the denominator. And so this answer is the same as that. And then here you can argue that the numerator is going to go to infinity and the denominator is going to go to infinity, but the numerator is growing much more quickly. X to the 4th is going to become a much bigger number than x, and so the whole expression should go to infinity. Again, if you don't see it at that point, you could take it one step further, divide one of those x's by one of them up there to be left with this, and now it's clear to see that as x goes to infinity, 2x cubed is just going to go to infinity. I mean, plugging in a large number into this expression is going to be a large number cubed times 2, so clearly that's going to infinity. All right. So one of the things you want to be aware of is sometimes, end behavior does not just involve going to infinity; it also involves going to negative infinity. So I mean, if I, for instance, take this last example, if I just said, let's make this 3a and this 3b. If I had done the limit as x goes to infinity, negative infinity rather, of 2x to the fourth minus x plus 5 divided by x minus 7, everything, the reasoning can follow exactly like it did above. Right, we can limit our attention to this ratio, and we can argue that that's the same as. But this time, since we're approaching negative infinity in the x direction, then imagining a big number like, negative a million. A negative a million cubed is a negative number times a negative number times a negative number, which is another negative number. And the fact that it's a million cubed makes it a big negative number. Timesing it by 2 keeps it as a big negative number. So it's negative infinity this time. So be conscious of that distinction as well.